Okay, then we will go back to this simulated experiment and then discuss the effect of dielectrics or dielectric materials. So I think you are not quite familiar with dielectrics, so I will explain it very soon. And then the reason why we discuss this dielectrics is the following. Try to remember the definition of the capacitance. Actually, not the definition, but try to remember how you calculated the capacitance of a parallel plate capacitor. And then we said that in order to increase the capacitance, we have to have the area large or the distance small. But then there was another factor, actually a constant coming into the equation, which was epsilon naught. We called it electric permittivity constant. And then, then it comes a question: can we actually make this epsilon naught larger, and then make the capacitance larger? Okay, we will discuss this after doing this simulation. Okay, here we have a battery connected to a capacitor, parallel plate capacitor, and this yellow stuff here, this is a material, dielectric material, I mean. Okay, let's take it away for a while, and then let me try back on what we have done previously. Okay, so I increased the potential to 1.5 volt. As you can see, the charges have accumulated on the two plates of the parallel plate capacitor. Remember that once you have the fixed potential, then the capacitance will be proportional to the amount of charge on each plate. Okay, and then how we could increase the capacitance of this parallel plate? The first method was increasing the area. You see that when you increase the area, the number of positive signs and negative signs are increasing, representing that the amount of charge is increasing. Okay, and then you can also reduce the distance between these two charges. So again, the number of charges are increasing. These were the two methods you could increase the capacitance. Okay, and then let's see what happens if you insert this dielectrics between these two plates. Okay, take a look. You see, okay, can you see that the number of charges on these two plates are again increasing when you insert this dielectrics? Okay, this is what the dielectrics will do when you insert it into the gap between the two plates. And as you can also see that inside these dielectric materials, there are pairs of positive and negative charges everywhere. This is the key element in being able to increase the capacitance by using this dielectric. Okay, I will explain this in the next slide. Okay, let me explain what dielectrics are. First, dielectrics are insulators, which means that charges will not really move. There may be small shifts, but they cannot really move. And then there are two types of dielectrics. First is the dielectrics with permanent dipoles, and the second is with induced dipole moment. The first is the dielectric permanent dipole. We learned about electric dipole, right? So each of them here are electric dipoles, but their directions are more or less random. But then once you apply electric field, what happens is that the negative sides are more or less aligned on the left side, and positive sides are more or less aligned on the right side. So here we can say that they are poled. So right side will be positive and left side will be negative under external electric field. And then the second type is the induced dipole. In this case, in the beginning there's nothing. In the beginning it's like just neutral, charge neutral sphere. And then once you apply electric field, each sphere split into negative and positive part and become dielectrics. Here, whether you have permanent dipoles or induced dipoles, the results are the same. Once in the electric field, on the negative side, effectively the negative charges will build up, and then the right side, the positive charges will build up, because in the middle, more or less, they are canceling. Okay, so this is the result here. So you apply external electric field E0 by using these capacitors, and then if the dielectrics are inside, effectively right in front of positive plate there will be negative charges built up, and then right in front of negative plate there will be positive charges built up. So then what will be the electric field coming from these additional charges? Positive here and negative here, so therefore electric field will be going this way, so that is this E prime. And then electric fields are vectors, so eventually if you are sitting inside this dielectric, you have to add these two vectors, and this the electric field this material will experience. Okay, so finally we can say that the electric field, total electric field actually becomes E0 minus E prime. Okay, and then why is it important? We will soon see. We will see the details in the next slide. But effect is that you actually have to multiply some constant when you calculate the capacitance. So then, if you can directly see that it is not actually changing the constant E naught itself, because E naught is a really fixed number. You cannot really change this constant, but effectively you can multiply by a certain number which is larger than 1. If this constant kappa is larger than 1, then we will have effectively the larger capacitance, and this kappa is in fact the ratio between the original electric field and then the final electric fields. And if you look at this figure, the final total electric field will be smaller than the original electric field, so therefore you can see that kappa always has to be larger than 1. That is why we could increase the capacitance by using this dielectrics. Okay. Then we will quantitatively discuss how this dielectrics can change the capacitance. Okay. We will first consider the case without dielectrics, and this is what we have already done. And there we use the Gauss law, so let's try again. So this is the parallel plate capacitor here, and then we have the Gaussian surface marked by red lines. And then let's use the Gauss law. Okay, the integration of the electric field over the Gaussian surface, while the upper surface and side surface becomes all 0, and we only need to consider the electric field at this location, which is E naught. E naught, the original electric field without dielectrics. So therefore is epsilon naught E naught multiplied by the area of the capacitor. And then how much charge is enclosed within this Gaussian surface? That is of course the total charge on the positive plate, which is Q. Okay, we write it as Q. So therefore we can summarize it using this equation. And then let's try to add these dielectrics. The figure is at the bottom here. And then we learned that when the dielectrics is inside the charged capacitor, the electric dipoles will build up and charges will accumulate right in front of the charged plates. So here we will have negative charges right in front of the positive charges of the plate. Okay, and then this, let's call this minus Q prime, and then the size of this Q prime is of course smaller than the original charge Q. It cannot be larger, right? So therefore we can now rewrite the Gauss law in this case using this equation. Now the total enclosed charge will be Q minus Q prime, as we have just said, and then the electric field between these two plates now is no longer E naught, but it is actually E, which is reduced compared to E naught. And then we can again summarize this using this equation. Okay, and then remember how we defined the constant kappa in the previous slide. That was the ratio between the original electric field and then the reduced electric field. So we can rewrite that the electric field, new electric field, is E naught divided by this constant kappa. And then let's insert the results. We just calculated two results. So first one is here, and then there's another one. And then you can see that this epsilon naught and A cancel out. So we get this relationship. Okay. And then let's try to insert this equation back into actually over here, over there. Okay. And then what do we get? So if you summarize, it becomes this way. So on the right side, instead of q minus q prime, we have q divided by kappa. And then the reason why I did this is because we do not want q prime in the equation, because we are not sure what q prime will be. Okay, and then now we can multiply this kappa on both sides, and then this is finally what we get. So take a look at this equation. How does it look like? It looks very similar to the Gauss law, except for this kappa, right? So what does it actually mean? So without dielectrics, the kappa will not be there, but when you insert the dielectrics, the kappa has to be inserted here. So which means that now when the dielectrics is inserted in the capacitor, everywhere whenever you have this epsilon naught, we have to replace by kappa epsilon naught. And then we said that kappa is larger than 1, so therefore the epsilon naught effectively becomes larger by being multiplied by kappa. Okay, and then if you remember the definition of the capacitance, which was proportional to epsilon naught, that is how the capacitance becomes increased. Okay, and then this is generally true for any shape of capacitors. We discussed this only for parallel plate capacitor, but same is true for all kinds of capacitors. Okay, and then let me finally throw in another question. Okay, what will happen if we insert a metal instead of a dielectric? Okay, and then in this case, let's assume that we inserted the metal in such a way that the metal actually does not touch the capacitor plate, right? So, and then, well, what will happen? Think about it, and we will discuss this in the classroom. Okay, let's finally make a summary of today's lecture. Let's check whether you remember or not one by one. From this lecture, you have learned the capacitor, which is a device to store electric charges. And you also learned the capacitance, which is defined as the charge stored per unit potential. Okay, and then you also learned that capacitors store energy in the form of electric charge or in the form of electric field. Okay, and then we learned how to calculate capacitance of our capacitor using the Gauss law. And then we learned how to calculate total capacitance for many capacitors that are connected together. Try to remember, we tried this for the case of capacitors connected in series and also connected in parallel. So if you combine these two ideas, you can calculate the total capacitance of many connected capacitors in any form, right? Okay. And then finally, we learned how the capacitance changes when a capacitor is filled with dielectrics. Okay, these are the things we have studied here. And these are the things we will study in the next online lecture. But just like always, I will see you in the classroom on Thursday. So please make sure before you leave this before you leave this website, please make sure you solve all the online quiz and then click submit. Okay, thank you.